Okay, well, we are moving into continuous time Markov chains for the first time, and these are still on discrete state spaces, and we really haven't done anything yet other than like preparatory work. We talked about some things we needed to know, like continuous distributions and PDFs and CDFs, the exponential distribution, the lack of memory property of the exponential. We talked about the gamma distribution. We needed to talk about the gamma function in order to do that. And we talked about a method of simulation for continuous random variables called the inverse CDF method, which is a lot of fun when it can be used. But you can't, for example, use the inverse CDF method on the gamma distribution because you can't write down the CDF in closed form, much less inverted. The same is true for the normal distribution and lots of distributions. So I was saying last time that, you want to get together a big toolkit of algorithms, and when you can't apply the simplest one, you go for the next simplest one. And we are going to hit a second algorithm today called the accept reject algorithm. But first, there are two claims I want to get out of the way. I guess right before that, I wanted to talk about how the relationships between the exponential and gamma distribution. So if we have x exponential with rate lambda, then we know that the PDF is lambda e to the minus lambda x for x greater than 0 or greater than or equal to 0. It doesn't matter. And it's 0 everywhere else. So I'm going to stop writing the piecewise part right now. And if you have x having a gamma distribution with parameters alpha and beta, the PDF there is 1 over this gamma function evaluated at alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x. And that's also for x greater than 0. So last time we saw that gamma of 1 was 1. That was our first of 3 properties of the gamma distribution. And so, check this out. If you're looking at a gamma distribution with alpha equals 1 and a kind of generic beta, then that means that the PDF is 1, that 1 over 1, the gamma of 1, beta to the 1, x to the 0, e to the minus beta x, and you're left with beta e to the minus beta x. And it lives on x greater than 0. And that's an exponential distribution. So we have that the gamma 1 beta distribution is the same thing as the exponential distribution with rate beta. So that was fairly easy to see, even if you didn't know how to define the gamma function. If you plug in alpha equals 1, and if you were left with 1 over gamma of 1, beta to the 1, x to the 0, e to the minus beta x, you know now that gamma of 1 has to be 1, because this is the exponential PDF that integrates to 1 as x goes from 0 to infinity. So if you multiplied in front by like 1/3, the integral will no longer be 1, it would be 1/3. So because you see the exponential distribution in this circle, that tells you that the stuff in the other circle has to equal 1, even if you never saw the definition of the gamma function. Okay, so I said I have 2 claims, maybe it's 3, and that was one of them. Claim 1 is that if you have x1, x2, out through xn, independent, and all with the exponential rate lambda distribution. So if you've had math stat or many kinds of stat courses, these are IID random variables. They're independent and identically distributed. And so we can write that as x1, x2, out through xn. A squiggly line has the distribution. Put the little initials IID on the top, and then the name of the distribution. So that's not a claim, that's just the setup. But my claim is that if you sum these, so if you let I go from 1 to n of xi, summing up IID exponentials actually gets you a gamma distribution. The first parameter is the number of exponentials you added together, which is n, and the second parameter matches that of the exponential distribution. So I debated for a long time today whether or not I was going to prove this. This is something you would prove in a math stat course, maybe some other courses as well. And to do it, we need moment generating functions. And those are not that hard, but this would be quite a diversion. So, but I also don't want to not prove it. Don't want to not prove it. Don't want to not prove it. I'm not going to prove it here, but right at this point in the video, I'm going to insert I'm going to talk about moment generating functions, defining them. You do not need this for Markov, but if you're interested, how to define a moment generating function and how to use it to get a distribution of a sum, and in particular, how to show this fact. This is just a little optional aside for anyone who wants to know how to show that the sum of exponentials has a gamma distribution. And the approach we're going to take is using moment generating functions, or MGFs. A random variable x has a moment generating function defined as follows. I'm going to call it big capital M for moment. I'm going to put a subscript x to attach it to the random variable. This is optional. And then it gets an argument, which is usually something like a U or an S or T. I'm going to use a T. And this is defined to be the expected value of e to the tx. And that is true whether x is discrete or continuous. And if x is continuous, which is what we kind of care about right now with the exponential, then this is going to be the integral from minus infinity to infinity of e to the tx times the PDF for x. This looks suspiciously like a Laplace transform. So it's not a Laplace transform, but it's like a Laplace transform. And so if you've had Laplace transform theory, you might believe the next statement. And that is that if you are given a moment generating function, you can actually recover the PDF, a unique PDF that goes with that moment generating function. And it's not nice. It's not a nice formula to write down, or I would write it. And even though this isn't quite a Laplace transform, if you'd like to read about that fact that you can uniquely recover the PDF and therefore uniquely recover the distribution, you should check out this book by Feller. So let's compute a couple of moment generating functions. Here in this video, I'm not even going to get into why it's called a moment generating function or what a moment is, because that is even more of an aside outside of our course. But if we want to compute the moment generating function for an exponential distribution, we're going to take the expected value of e to the tx, and this is the integral in general minus infinity to infinity of e to the little tx times the PDF for x. But because we have an exponential distribution, this is the integral from minus infinity to infinity of e to the tx lambda e to the minus lambda x dx. To integrate this, I'm going to combine the e's, and I'm going to write this as 0 to infinity lambda e to the minus lambda minus t x. You can probably imagine combining those exponents in a slightly different way. But what I've done now is gotten it to look kind of like an exponential distribution. So this thing is going to blow up. We want this whole entire exponent to be negative. And because of the negative out front, that means that we want lambda minus t to be positive. So that means we want lambda to be greater than t, but t is the argument of the function. So maybe we should say it the other way. We want t less than lambda when defining this moment generating function. And now you can either integrate this from scratch using your integration skills, or I can kind of integrate it without integrating by making it look like the exponential PDF that it's almost looking like. If I had 0 to infinity of lambda minus t e to the minus lambda minus t x dx, then that would be an exponential distribution PDF with parameter lambda minus t. And fortunately, lambda minus t is positive because that is a requirement for the exponential parameter. But that's not what I have in the line above. I forgot my lambda, so let me put that in. And I also put in this extra lambda minus t, so let me compensate and put that on the bottom. And now it is the line above. And now this is the integral of the exponential PDF with rate lambda minus t, and it integrates to 1. So to summarize, the moment generating function for this exponential distribution is lambda over lambda minus t, and this holds as long as t is less than lambda. You can do something very similar. I'm going to not go through this, but it's just as quote unquote easy to start with a gamma distribution and to find that the moment generating function there, if you use our parameterization of the gamma distribution with alpha and beta as we have used them, this is going to be beta over beta minus t to the alpha. And this is also going to be restricted to having t less than, in this case, beta. So how does this relate to sums of random variables? Suppose that I have x1, x2 out through xn, iid, exponential with rate lambda. And I want the distribution of the sum. So I'm going to give that a name. I'm going to let y be the sum as I goes from 1 to n of the xi. So we just talked about how these moment generating functions uniquely determine the distribution, and that's because it's relevant and convenient here. We're going to find the moment generating function for y in terms of the moment generating function for x. So I'm going to call this m sub y of t. It's defined to be the expected value of e to the t y. Right now, I'm not assuming an exponential distribution in what I'm writing. I can replace that capital Y with the expected value of e to the t sum of the x's. That can be written as a product of e's, the product as I goes from 1 to n of e to the t xi. And by independence of the different terms, because I am assuming IID random variables here, even though I'm not talking about the exponential yet, I can bring that product outside. You might be familiar with like breaking up a product like the expected value of x and y multiplied if they're independent. I'm just doing that kind of with a bigger product. And this is the moment generating function for xi. So this is going to be the product as I goes from 1 to n of the moment generating function for xi of t. But how do you find the moment generating function for xi? You have to integrate. I'm just going to get another color here. You're going to have to integrate if it's exponential, say, no, anything. You're going to integrate from minus infinity to infinity, e to the tx times the PDF. And if they all have the same PDF, so rather than using xi here, I'm just going to use f sub x, then the integrals are all going to be the same. So by the identicalness of the xi, this is going to be the moment generating function for one of them to the nth power. So what we've just shown is that if you sum up IID random variables, the moment generating function of the sum is one of the original moment generating functions to the nth power. And now let's use that with the exponential distribution. So if we have x1 through xn, IID exponential with rate lambda, then we know the moment generating function of any one of these is lambda over lambda minus t, and this holds for t less than lambda. It's just not defined if t is greater than or equal to lambda. So if we let y be the sum as I goes from 1 to n of these IID random variables, then we just showed that the moment generating function for y in this IID case is the moment generating function for one of them to the nth power. So just a few minutes ago, we found the moment generating function for an exponential. It was, oh, it's right above us. It's lambda over lambda minus t, and this is raised to the nth power. And this holds for t less than lambda. And this looks a lot like beta over beta minus t to the alpha, which was the moment generating function for the gamma distribution. In fact, we can say this is the moment generating function for the gamma distribution. Instead of alpha, I have an n, and instead of beta, I have a lambda. And because moment generating functions uniquely determine the distribution, and y has this moment generating function, we can say that y, which is the sum of the x's, has this gamma distribution with parameters n and lambda. Let's go back to the class. Claim 2. Oh, yeah, actually, one thing I did want to do was show you this. So here I am in R, and I wrote a little script that's huge because just I know I still need to post my last ones for you. What I'm about to do really takes 3 lines, but I was doing fancy stuff. And so what I did was grab 100,000 exponentials, each with rate 2.2. And that's not true. I grabbed 1,000,000. So I made a matrix that was 100,000 by 10, filled them with exponentials with rate 2.2, independent of each other. And then I computed all the row sums, which gave me 100,000 sums, 100,000 numbers that came from adding up 10 things for each row. And this is the histogram of 10 exponentials added together, repeated 100,000 times. And as I said, the rate was 2.2. And if I want to superimpose the gamma PDF on this, that the appropriate PDF would be the gamma 10, comma 2.2, and do that in the next step. And there it is. So it doesn't look that bad. So yeah, this is what I decided to do instead of proving the moment generating function stuff in class. We could see it at least through simulation. And I personally use simulation all the time to do theoretical work, especially when I have a conjecture or something I'm trying to prove in my research and I just hitting my head against the wall for months sometimes. I will then simulate what I'm trying to prove just to give myself a little more confidence, or destroy everything, one or the other. And then usually I can end up proving it or not. Very, very binomial. So this is an example of summing exponentials to get the gamma. Okay, so claim 2 is that if you take x1, x2 out through xn, independent and identically distributed, so IID, exponential with rate lambda, and you look at the minimum, so define y to be the minimum value, until you observe those n random variables, they're random until you observe them, and so is y. You don't know what the minimum is going to be. And to see that y has its own distribution, simulation is great for explaining what's going on here. If I were to, I'm not going to switch out to R for this one. So if I had an exponential distribution with rate lambda, so the PDF is lambda e to the minus lambda x, and I ran the inverse CDF algorithm to simulate some values, and maybe I simulated 10 values, and then I recorded the minimum and then started all over. So maybe 100,000 times I got a sample of size 10, recorded the minimum, and then threw everything out. And then with the collection of minimums, I can make a histogram. It has its own distribution and its own shape. And that's what we want to know about now. So let's find the distribution of y. I think it's easiest when you're working with minimums or maximums to look at the CDF. So let's consider the CDF, the cumulative distribution function for y, CDF. This is the probability that y is less than or equal to some little y. I don't really need to write this, but maybe it'll be a little more illuminating to see the minimum in there. So I'm just going to replace that capital Y with this minimum. And what do I know about? I know about the individual x's. So when computing a CDF, a cumulative distribution function for a minimum or maximum of random variables, the goal is usually to try to rewrite this in terms of the individual random variables. And so I like to look at like a number line, and this y is just some argument, it's a fixed number. And I like to think about how the x's, if you were to sample them, how they would fall on this number line in a way that would make the minimum below y. And so if these are x's that I was sampling, this is a sample of size 4, 5, 6. The minimum is right here. And if I had a sample like this, not that they should look equally spaced or anything like that, the minimum is down below y. And if I had one here and all the rest up here, the minimum is below y. And so looking at the minimum in this way and trying to figure out where the x's are is kind of difficult, but not if you turn this probability around. So I'm going to look at the complement of this event. I'm going to take 1 minus the probability that the minimum of x1, x2, out through xn is greater than y. Because if I do the same sort of thing, number line, stick the y down there, there's only one way for, well, there's a lot of positions, but overall there's one way for the minimum of your data to be greater than y. And that's if and only if every single individual data point was greater than y, every single x. So going back up here, this is 1 minus the probability that x1 is greater than y and x2 is greater than y and out through xn is greater than y. And they're independent. So I get to multiply those probabilities, break it up into a product. So by independence, this is 1 minus the probability that x1 is greater than y, probability x2 is greater than y, ... These probabilities are all the same. If you have a sample, the individual random variables are not the same, but they all have the same chance of being greater than y because they come from the same distribution. One thing I could do here is, I'm not going to do it, but I could rewrite this as 1 minus the probability that x1 is greater than y to the nth power. And then I need that quantity. But rather than doing that, I will just write out what we have. So remember the CDF for the exponential, so the probability that xi is less than or equal to x for an exponential with rate lambda. This is 1 minus e to the minus lambda x. But up here, I have tail probabilities, so I want 1 minus that. And so I get 1 minus e to the minus lambda y times e to the minus lambda y times e to the minus lambda y. I get n of those. So you're seeing where the power comes in. I'm going to add those exponents and I'll get e to the minus n lambda y. This is the CDF of the minimum of NIID exponentials with some rate lambda. And what is this a CDF of? We're seeing it right here. It looks like the same CDF, except the lambda has been replaced with n times lambda. And that means that this y, this minimum of x1 through xn, is actually exponential with rate n lambda. And that's the end of claim 2. I think it's a little surprising that it's exponential. That doesn't usually happen for most distributions, but I think the rate parameter is not surprising as it relates to the original rate parameter, because the original x's come from a PDF that starts at lambda and goes down exponentially. And if you were to take a sample of some size and then just grab the minimum and do it again and just grab the minimum and do it again and just grab the minimum, your points are going to be more clustered down towards 0. Which means that if you were to think about their distribution, the histogram is going to be squished down towards 0, but taller so that the total area is 1. And that is what is happening. We are starting at n lambda and going down exponentially, but because the total area has to be 1, we're going to shoot down a lot faster. So maybe, I don't know, maybe you did see it coming, but maybe you didn't see the exponential distribution coming when looking at the minimum. But at least the rate parameter being larger than it was for the individuals makes sense. I never planned to have 2 simulation breaks in a row, but this was all supposed to be done yesterday. So it's time for a simulation break. Do, do, do. Okay, so I want to simulate from the gamma distribution, and it's a continuous random variable, and I cannot write down its CDF in closed form. So I can't use the inverse CDF method. So I have to move on to something else. And what I'm going to do is use something called the accept reject method, which is attributed to John von Neumann. And this method can be used in the discrete and continuous cases. Everything I'm going to talk about today, I'm going to describe it in terms of continuous random variables, but this all could be for discrete distribution. So I have a target. When I say target, I mean the thing I want to simulate from. So this is some PDF like f of x, and I'm going to assume it's continuous, but I do not have to assume that for this algorithm. And I want to simulate values from this PDF. So again, by target, I mean this is the probability density function that we want to simulate from. So the accept reject method has like what I call pre-algorithm steps. You need to choose another function that has some nice properties, and then you're ready to talk about the algorithm. So I will call this, lots of quotes today, pre-algorithm kind of steps or setup. And I think I'll describe it in kind of the classical way, but I always implement this backwards. What does that mean? Okay, so number one is, you know what? I want to be a little more specific here. So suppose that F has support. I've mentioned this before. This is not really the domain. It's the place where it's interesting and non-zero. And I'm going to call that S. Why not? Looks like a state space, but that's okay. So S might be the interval from 0 to infinity. For a uniform, the interval from 0 to 1. For a geometric, it's the set of integers 0, 1, 2, 3, 4 on up, or maybe not including 0. So the target PDF has some support. And so you want to find a function g of x, such that g of x is greater than or equal to f of x for all x in the support. And you can't just take any function that bounds your target. You need to be able to integrate it and get something finite. And you're concerned about integrating it on that support set. So I'm going to integrate over, I don't know if everyone has seen notation like this, I'm going to integrate over that set. This is standing in for 0 to infinity, or 0 to 1, or negative infinity to infinity. It's just whatever the limits of integration are for the PDF. And I'm going to integrate the function g, which is not a PDF. Okay, and we need that to be finite. So step one is to choose like a bounding function that's integrable, but that's not bad. What's bad is that it won't probably won't work for step two. So we're going to take this constant, and because the PDF is non-negative, g being above it is also non-negative, and it integrates to something that's also going to be non-negative. And so if we define h of x, if we define this to be 1 over c times g of x, this is a PDF. This is something that's non-negative and integrates to 1. It's a PDF on that support set. And step 2 is that we need to be able to simulate values from h. So you're not really just free to grab any bounding function g. It needs to be nice enough that you have another algorithm to do this part from h. For example, for this step, you might use the inverse CDF method if you can. And we're going to do an example today where we're going to do accept reject on the gamma distribution. And yeah, we'll be able to, well, you just wait. Let me tell you what the algorithm is. So here it is. That was pre-algorithm. Here is the accept reject algorithm to get one draw from the target. So first you simulate or draw, as I like to say, you get a number from, well, I'm going to call it y, from, I'm just going to use the distribution sign, with the distribution described by the PDF H. Does that notation make sense? So I'm not writing the name of a distribution, but y is from the distribution that has PDF H. And part of our setup was we presumed we could produce values of y. And then the next step is to simulate or draw a uniform. I'll call it U, uniform 0, 1, which we already assume we can do from a random number generator. The third step and final step, depending on how you want to clump these together, is if U is less than or equal to f of capital Y over g of capital Y, you're going to output Y. Otherwise, you delete everything and start over. Delete Y and U and start over independently. So you're starting over independently. And also, I should say that this U should be independent of Y. Yeah. So I really, really, really want to prove this. I'm going to push it to the end, which might mean it gets pushed until Monday, because I'm afraid I won't get to everything you need to do the current homework. So we're definitely proving this, but let's see how to use it. I did say that I do those pre-algorithm steps backwards, and probably most people do. So let's try an example. I want to simulate, from a gamma distribution, the gamma with some parameters alpha and beta, which have to be given. They're given numbers. And we're going to bound this thing, and it's going to change depending on the shape of the distribution. So I just want to consider right now, I just want to consider one kind of shape. And that is the shape when alpha is greater than 1. We talked about shapes last time. When alpha is greater than 1, this distribution has an x to the alpha minus 1 and then an e to the negative beta x. So it goes up for a while and then comes down. And so that's kind of a generic looking gamma distribution, a little flat. Usually they look taller. I guess, yeah, my scale is off. So this is going to be the target, which is f of x equals 1 over gamma of alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x for x greater than 0. So to start to set up for the algorithm, we need to find something above it that we can integrate, and that when we do, we can draw from what's left, or the PDF we made out of that. That's really hard. I would instead choose a PDF you can draw from. So choose the H and then try to find the G. So I'm going to choose H, not G. And then we'll go back and find G. And I'm just going to choose an exponential distribution because we can simulate from that using the inverse CDF method. In practice, you're probably going to be simulating from some arbitrary distribution that doesn't have a name. And that part where you need to be able to draw from that candidate distribution is probably going to be a black box generator from your software. But I'm going to choose h of x to be, so I'm going to try to take the exponential part of this. I'm going to let it be beta e to the minus beta x for x greater than 0. And what do we need? So remember that g of x is going to be c times h of x, because h of x was 1 over c times g. And we need f of x to be less than or equal to g of x, i.e., we need f of x over g of x to be less than or equal to 1. But if you plug in the g of x as ch of x, this is the same thing as saying, i.e., we need f of x over h of x to be less than or equal to c. So I chose a distribution I wanted to kind of propose values from. And now if we can find an upper bound on this ratio, we'll have a c, which will then define the g. So let's look at f of x over h of x. This is 1 over gamma of alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x. And down here I have beta, e to the minus beta x. And when I cancel some stuff, I get 1 over gamma of alpha, beta to the alpha minus 1, x to the alpha minus 1. And that's bad news because this is constant. This is increasing. We can't bound this on 0 to infinity. Which means I had a poor choice for my candidate distribution. But I think we can still use the exponential. Let's just look at a more generic rate. So I want to try h of x equaling some lambda e to the minus lambda x. And then if I look at f of x over h of x, I will get 1 over gamma of alpha beta to the alpha over lambda. What am I doing? X to the alpha minus 1, e to the minus beta minus lambda x. And this has that kind of gamma shape, as long as I do need this to be positive, the thing inside the parentheses. I need the whole exponent to be negative. Otherwise, this thing is going to blow up and not, I mean, it's going to blow up. So we need beta to be greater than lambda. And what that's going to mean in the long term, the lambda parameter, the e to the minus lambda x, is going to go down as you go out to infinity a little bit slower than e to the minus beta x. So the candidate distribution is going to need to have like fatter tails. Otherwise, you'll get that unbounded problem. Okay, I think I will spare you the, I wanted to maximize this. I wanted to find a C. So I actually maximized it. And I did that by taking the derivative with respect to x of x alpha minus 1 e to the minus beta minus lambda x. I did a product rule and set it equal to 0. And I got that the x that makes that 0 is alpha minus 1 over beta minus lambda. So that's where we maximize the thing that I've circled. And you could check with the second derivative that you didn't minimize it if you wanted. So this means that my C is 1 over gamma of alpha, beta to the alpha over lambda. I'm plugging in for x, alpha minus 1 over beta minus lambda to the alpha minus 1, e to the minus beta minus lambda times alpha minus 1 over beta minus lambda. So I do get some cancellation out there, but it's just a big funky constant. We had step 1 where we want to simulate a y from the exponential with rate lambda. Oh, by the way, we have to choose a lambda so that lambda is less than beta. And we want to simulate a u uniform 0, 1. And if u is less than or equal to f, which is the gamma PDF, evaluated at the y you chose over g, or you can write this denominator in terms of the c and h. You want output y. Otherwise, start over. And I want to prove this next time. And I also want to talk about good choices for the candidate distribution. You would like it to be as close as possible to the target. This uniform thing we're doing, so if we have a target that looks like this, and then like a g, so that's supposed to be the exponential but not normalized, multiplied by the c. Then once we draw a value from the properly normalized g, when we turn it into an h in an actual PDF, we're taking a uniform and we're trying to figure out whether it falls here versus here. Like this ratio of f to g. And so if your g is way high, then you're not going to accept very often. So you would like the c to be as small as possible. And you ideally would try to mimic this shape if you can, but usually you can't, or then you wouldn't have done this in the first place. If you took your h to be the target f, which you wouldn't do because otherwise you couldn't simulate from it and you wouldn't be doing this, then your g would also be that target f because it's already normalized. And you would be looking at if the uniform is less than or equal to 1, which it always is. So if you could draw from the gamma distribution and run it through accept reject, you would always accept it. And that makes sense. So I keep saying I want to prove why this works next time. I also want to talk about like the expected number of steps until acceptance. The distribution of the number of steps until acceptance is a geometric. We have like draw this, draw this, check this. Yes, success, no failure. Otherwise, start all over. And we're going until the first time we get a success. So we'll talk about the number of steps to first acceptance as a geometric random variable. It's going to be the geometric that starts from 1. And the p, the probability of acceptance or success, is 1 over c. So that's another place where you can see a large c is not a great idea because you will not accept very often. So yeah, I'm going to jump ahead. I'll come back to this stuff. Otherwise, the whole homework would have to be really accept, reject, and inverse CDF because we really haven't had time to. I'd rather get a couple more topics on there. But I definitely want to come back to this. Let's talk about continuous time Markov chains on a discrete state space. Or usually I say process and only chain if it's discrete time, but no one cares. I mean, I don't even know why I do that. Continuous time Markov process or Markov chain on a discrete state space that I'm going to continue to call S. S. I'm going to change up our notation for the Markov chain a little bit. So before we had a sequence xn, and n went from 0 to infinity, and that looks very discrete. I'm going to go from n and m's to t's and s's. Not that there aren't people out there using like discrete, t for discrete things, but I think definitely, n's and m's look discrete. It would be weird. It would be weird to have a process like this in continuous time. So I'm going to move to t's and s's, and I'm going to do something else just to make it extra clear. So not only am I going to move to t's, but I'm going to move, some people do this, some people don't. I'm going to change the notation to x of t to be really clear about the difference. And now t is everything greater than or equal to 0, all real numbers greater than or equal to 0. So this is my notation for discrete time and continuous time. I should probably define the Markov property. I think I'm going to save that one as well in favor of getting to some more concrete things and exercises like the current homework. But we already talked about what that should be. And that is you have a process evolving over continuous time, which means that you're switching places, you're switching discrete states at random time points. And so I will write it down next time, but the Markov property says if you just come in at any time t, then where you go next depends only on where you are. I think you're not going to be surprised about this definition. So rather than do that right now, I want to define a counting process. This is a special kind of stochastic process that usually gets its own letter rather than x of t. We call it n of t, capital N of t. So a counting process, and here's the whole collection. So n of t, or t greater than or equal to 0, is a stochastic process that counts, it accumulates events. So it counts a number of events that have happened up to and including time t. So if the event is like arrivals of a person to a store, this is going to be some sort of process that we're going to usually, the convention is to start it at 0, although you can probably rewrite everything to start at a different value. But this is just going to be your count axis, and this is going to be time. And we're going to start at 0 and go for some random amount of time at 0, in which point we'll jump up. Actually, we don't have to jump up by 1. We can jump up by whatever. So jump up by some number, but usually it's going to be 1 for us. And then we'll stay flat for some random amount of time and jump up by some number. And so this is a step function looking thing. And if you look at so n of t is a random variable. It is the number of arrivals by time t. In this picture, n of t is 2. I had 2 arrivals by time t. And so this is a random variable. And we're going to talk a lot about increments of the process. So if you have like 2 time points, s less than t, then n of t minus n of s is the number of events. And because we defined it going up to and including time t, this is the number of events that occur in the time interval open s to close, t. So yeah, if you look at some interval and you look at the value of the process here and subtract, then you'll get the number of times it jumped. That is an increment of the process. We're going to start using phrases like stationary increments. So this may or may not be Markov. I don't know what's generating the people coming in to the store and whether or not it's Markovian. But we're going to look at some specific kinds of counting processes that are Markovian. We don't know about stationary or limiting distributions in the continuous time setting, but I can already tell you that this is not going to have either because it's always increasing. Maybe draw the steps. So it just keeps going up unless you have some kind of top on the system, like a queuing model with a waiting room. But I mean, you might have a limit then that you approach the max capacity or something. But in general, this does not have a stationary distribution, whatever that is in this context, and a limiting distribution. Okay, so the particular counting process I want to talk about today is arguably the most famous continuous time discrete state space process. It is the Poisson process. And first, I want to remind you about a Poisson random variable. So that is a discrete distribution, a discrete random variable x is said to have a Poisson distribution with a parameter that's almost always called lambda that needs to be positive if x has the probability mass function the probability that x equals x is going to be e to the minus lambda, lambda to the x over x factorial for x equals 0, 1, 2 on up, all non-negative integers, and it's 0 otherwise. This is what we'll write. We'll write x has the distribution Poisson lambda. And we're going to start seeing a lot of e's, exponentials and Poissons. So 2 things to know about e to the x that will be helpful. About e to the x. Number 1 is to recall how you get it from a limit. The limit as n goes to infinity of 1 plus x over n to the n is how you define e to the x. So this is going to 0, so the thing in the parentheses is going to 1, but you don't get 1 to the n because that n and the exponent is moving at the same time. You get this cool balancing act where you see e to the x. And the second thing is the Taylor or Maclaurin series expansion. We're going to use this a lot. So e to the x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and we can put this all together and say this is a sum as k goes from 0 to infinity of x to the k over k factorial. And that power series there will converge for all x. We don't need like an x between 0 and 1. So maybe it's been a while for some of you, but yeah, those are things from calculus. All right, it is time. No, it's not. Before we define the Poisson process, I wanted to talk about the expected value. So if x has a Poisson distribution with parameter lambda, the expected value of x, this is discrete, so this should be a sum over x of x times the probability that x equals x. And this distribution runs over the specific x's from 0 to infinity. X, and the PDF is e to the minus lambda, lambda to the x over x factorial. And there's 2 ways to, I think, at least 2 ways to approach this sum. One is to do the trick that if you've had my math stat class, all that integrating without integrating and summing without summing stuff would work great here. We did it here a couple of times when we had to compute some quantity involving the geometric, but it wasn't a geometric distribution until we added in some constants. So the other thing is to know the Taylor series expansion for E. First thing I'm going to do is take care of that x, because when x is 0, the term is 0. So this starts from 1, really. X times e to the minus lambda, lambda to the x over x factorial. And then that x can cancel with part of the x factorial. So I get e to the minus lambda, lambda to the x over x minus 1 factorial. And so if you want to make this look like another Poisson distribution by putting in and compensating for constants, that's great. The other option is to pull out the e, and I've got the sum from 1 to infinity of lambda to the x over x minus 1 factorial, kind of looking like the E series, but it's not starting at 0, and I have that x minus 1. So I'm going to pull out a single lambda, and then x goes from 1 to infinity, lambda to the x minus 1 over x minus 1 factorial. And if we re-index that, this is just the power series for e to the lambda. So we get lambda e to the minus lambda, e to the positive lambda, so we get lambda. The expected value of the Poisson distribution is just that parameter. That's probably not new to a lot of you. But now we're ready to define a Poisson process. This is such an important process. We're going to spend a lot of time on this because it's a base for a lot of interesting processes, especially processes. Well, I'm going to get ahead of myself. So let me just define the Poisson process. And I've got 3 ways to define it, and they're all equivalent. And part of what we're going to do for the next few classes is show the equivalence between the definitions. And I think it's worth it to see all 3 definitions because depending on what you're trying to solve, each one comes at it from kind of a different way, and I think I personally use all 3 definitions all the time. So this is definition 1 out of 3 of a Poisson process. So I'm moving from just a Poisson random variable to something being indexed in time, something evolving over time. And we're going to start with a counting process. So the counting process, N of t, is a Poisson process and so the Poisson distribution has a parameter called lambda, and in this context, it's always called a rate parameter. So with some rate, lambda greater than 0, that is a parameter of the model, if 3 things are true. So I'm going to do I, double I, and triple I. The first thing is really a matter of convention and could be changed, but everything would be really messy without it. And that is that the number of events counted by time 0 is 0. That's not that important to have that. The second is that the process N of t has, and I'll define this, but what we call independent increments. The process is accumulating things, events, people. And so where you are at some time t is definitely not independent of where you were at an earlier time, but the numbers of arrivals in between are independent of the number of arrivals in a non-overlapping time interval. So formally, I would say that for times 0, I'm going to call that t0 is 0, less than t1, less than t2, yada, yada, less than tn. The random variables n of t1 minus n of t0. So that's the number of arrivals between time 0 and time t1. And the number of arrivals between time t1 and t2 out to the number of arrivals between time tn minus 1 and tn. These are random quantities. These are non-overlapping intervals of time, and these are random variables. So how many are going to be in here versus here? These are random variables. So these are independent. Get rid of those. That's the assumption for this Poisson process. And finally, I've got a triple I, and this is where the Poisson distribution comes in. And so I'm going to say for any s or t greater than 0, I sometimes go back and forth on this. I made a mistake when I first wrote down the increment before because I was thinking of it this way. The number of arrivals in the interval of length t that starts at s. So this is a random variable, and it's the number of arrivals in the open interval s to the closed t plus s, because the counting process is defined as the number of arrivals up to and including the time you're looking at. So we're going to go all the way up to time s plus t, and we're going to take away the stuff below s and even at s if there is one at s, but that's not going to happen with the continuous times. And so I didn't finish this statement, but this has a Poisson distribution. And the parameter is the rate parameter given for the overall process times t. And t is the length of the time interval we're considering. So I could have written this like n of t minus n of s and made sure s was less than t, and then had a Poisson lambda t minus s. But I like the way I've written it here better. So specifically, Come on, go away. More specifically, if you are looking at some time s and some later time s plus t, so you have an interval of length t, and you are looking at how this process is incrementing, the way I've drawn it, it looks like there's an arrival like right there, and right there, 3 arrivals in that interval. The next time you make a realization of that process with new random input, there'll be potentially 0 in that interval or 9 in that interval. And that's a random variable that's going to be Poisson. And the parameter is lambda times the length of the time interval. And we saw that the expected value of a Poisson is the parameter. So we'll expect more values when t is larger and less values when t is shorter. This property is known as a stationary increments property, but by writing that, that's not descriptive enough. But the distribution of the number of arrivals in here, or any increment of time, does not depend on where that interval is. It only depends on the length of the interval. So if you take this interval from s to s plus t and slide it up here, if it still has length t, you still expect the same distribution for the number of arrivals, not changing in time. Yeah, so let us note. I love noting things if you can't tell. One thing is that n of t itself is an increment. It's n of t minus n of 0, because n of 0 is defined to be 0. And so this is a Poisson random variable with parameters lambda times t. The number of arrivals up to time t is assumed to be a Poisson random variable. And from this, I know that the expected value of n of t, we saw that the expected value of a Poisson random variable is just the parameter. Same here, we'll get lambda t. And I said this before, but I just want to write this down. So for s and t, not true, for s less than t, n of t minus n of s is Poisson with parameter lambda times the length of the time interval, which is now t minus s. Just another way to write what we wrote, we wrote it. Let's try some, just a couple of calculations, like numerical calculations. So suppose that, and when you do things with the Poisson process, you really want to take advantage of independent increments. You're almost always trying to rewrite things in terms of increments. But suppose that n of t is a Poisson process with rate lambda. So number one, if we want to know the probability that n of 3.2 is 5, then note that this is an increment, right? It's n of, you don't have to write this, I'm going to write it again though. It's n of 3.2 minus n of 0. This is a Poisson random variable with parameter 3.2 times the original lambda, length of the time interval times lambda. And so you just want to use the Poisson PMF. This is e to the minus 3.2 lambda, 3.2 lambda to the 5th power over 5 factorial. Let's do a joint probability. What is the probability that n of 3.2 is 5 and n of 1 is 2? At first, this may look like we're going to have a problem without an initial distribution, but we do kind of have an initial distribution. This is the same thing. I was saying just a moment ago, you want to take advantage of independent increments. This is the same thing as having one arrival by time 2, and then between time 2 and time 3.2. So the increment is 3 more. And then you can say, I'm going to use independent increments. And this is the probability of n of 3.2 minus n of 2 equaling 3 times the probability that n of 1 is 2. And so this is a Poisson random variable with parameter 1.2, subtract, times lambda. And this is Poisson with parameter 1 times lambda. So the answer here is going to be e to the minus 1.2 lambda, 1.2 lambda to the third over 3 factorial times e to the minus lambda, lambda squared over 2 factorial. So definitely taking advantage of independent increments all the way. Let's do a conditional probability. Before that, let me do, what is the probability that n of 3.2 is 2 and n of 1 is 5? This is an increasing process. So this is saying there was 5 arrivals by time 1. And then when you moved up to time 3.2, there was a total of 2 arrivals, but that can't happen. We already have 5. Thank you. And one more. Let's do a conditional probability that n of 3.2 is 5, given that n of 1 is 2. So one thing, I think we did, I got that right. One way to do this is just to go by the definition. This is the probability of one of those and the other one over the probability of the one after the given line. And we did this one in step 2. So if you just go strictly by the definition, you'll get there. But I would just think about what's happening here. So here's time. By time 1, we've had 2 arrivals and only 2 arrivals. And now we're looking at time 3.2, and we want a total of 5 arrivals. So given that there were 2 up to time 1, the probability that there's going to be 5 by the time we get here, this is just the probability that we get 3 arrivals in that interval. And that's exactly what you're going to see if you write it out the long way. If you write out the wrong way, you get this times the probability of this over the probability of this, and those probabilities cancel, and you just get what we have here by common sense, quote unquote. Okay. So you know what? I'm going to do one more here. What is the expected number of arrivals at time 3.2 given the number of arrivals at time 1 is 2? This one's a little tricky, or not tricky, but this requires a little bit more thought. So we've already had 2 arrivals by time 1. We want the expected number of arrivals by time 3.2. So we already have 2. And then we want the expected number of arrivals in this interval. Let me put this down here. This is going to be 2 plus the expected number of arrivals in this interval. And that interval has length. That's what I did before. I feel like I subtracted wrong before. That interval has length 2.2. So this is 2 plus 2.2 lambda. Sometimes you might see people, myself included, write that this is equal to 2 plus the expected number of arrivals by time 2.2, because that has the same distribution. That's the number of arrivals in an interval from 0 to 2.2. Not that this random variable is going to equal this, but they have the same distribution. They act the same, and they have the same expectations and variances and things. Okay. I need to decide if I'm going to define a Markov process in continuous time or try to get the proof for accept reject. I think that maybe I should do the continuous time definition for a Markov process. So I think I'm frozen, but I'm hoping you can hear me. Oh, I'm back. Here's a definition, a formal definition, finally, for a continuous time Markov process and what the Markov property means. A continuous time process. We're using these n's for these kind of counting step-up ones, but in general, I'm going to use x of t on a discrete state space S is a Markov process if it has a Markov property, which we're about to define, is a Markov process if for any time steps, we're going to need a bunch of them, just like before we had times 1 through n and then n plus 1. So for any S1 greater than or equal to 0, less than S2, less than up to less than Sn, less than some S and T, those are the two special points at the end. And for any I1, I2, these are going to be the states, IN, I, and J in the state space, we need the probability that the process at time t is equal to j, given that at time s, it's equal to I, at time Sn, it's equal to In, down to at time S0, it's equal to I0. We just need this to equal what you expect, just that last time step. The Poisson process is a Markov process. Hopefully, or we wouldn't spend so much time on it. So the Poisson process is a Markov process. And if I wanted to prove that, well, let's prove it. I'm going to let n of t be a Poisson process with rate lambda. And I want to look at this sort of thing. And just to make this go quicker, because these lines are long and I don't have much time left, I'm just going to fix n to be 3. The proof is not going to change at all. So just so these lines don't get ridiculously long, I'm going to look at the probability. Oh, this has to hold wherever the conditional probabilities are defined. So if one of them is undefined, but the other one is, you have not destroyed the Markov property. They have to be the same only when they're both defined. So the probability that n of t is some j, given n of s is some I, n of s3 is some I3, n of s2 is some I2. I'm regretting even going up to 3 right now. S1 is some I1. We want to show that that's equal to this conditional probability. So you want to do what we were just doing in those numerical examples. I would write out the definition. This is a big fat intersection. It barely fits over the probability of the second stuff, the stuff after the line. And we know how to do these. So how would we do the top one? I would look at the increment down here and say that this is n of S1 equals I1, and then n of S2 minus n of S1 has to equal I2 minus I1, just like we did those other more concrete looking things. I still didn't leave myself enough room. I am out of time. I'll pick that up, but you're going to write this out the same way we did it when we just had like 2 time steps and this, and you're going to see a lot of cancellation. And we'll see that, and we're going to start off by proving the accept-reject algorithm does what it says it does next time on Markov processes.
Thanks. And go.